So we can start now, no?
Yeah, please.
Okay, fine. So good evening to all the esteemed members of the Ocean Society of India, ladies and gentlemen. The Ocean Society of India conducts invited talks as a part of the OSI webinar series once in every month. And this talk is arranged from eminent scientists, engineers, academic professionals working in the broad areas of atmospheric and oceanic sciences, ocean engineering and technology, and allied areas. So this webinar series is primarily targeted for students, researchers, scientists, engineers, and working professionals in the field of atmospheric sciences, oceanic sciences, ocean engineering and technology, with a motive to impart and improve the knowledge benefiting the OSI community. So I request all the members to actively participate in all the webinars and get involved in all lectures under the OSI webinar series that is held once in every month. So on behalf of OSI, it is my proud privilege to welcome today Dr. Basanta Kumar Jena, Scientist G and Project Director at NIOT Chennai, for this invited talk today. Dr. Basanta Jena will be delivering a talk on the topic Indian Coastal Ocean Radar Network and its application. It's a topic of relevance for the engineers and scientists working in the field of oceanography, ocean engineering, and allied areas. Dr. Basanta Jena has completed his master's degree in physical oceanography and a doctorate degree in marine sciences, specialization in oceanography from Berhampur University, Odisha. He worked as a research scholar at CSIR National Institute of Oceanography, Goa, from 1993 to 1998, and thereafter joined the National Institute of Ocean Technology, NIOT, Chennai, since 1999, and presently holding the position of Scientist G and Project Director. Dr. Basanta Jena was very actively involved in the establishment of coastal observation systems along the Indian coast, including Andaman Islands, under various plants and industrial projects. So as a member of NIOT Coastal and Environmental Engineering Group, he has been instrumental in the establishment of the coastal high-frequency HF radar network along the Indian coast. So five pairs of 5 megahertz and 1 pair of 12 megahertz systems are being continuously operated under this program. He played a major role in hydrodynamic and sediment modeling studies towards the construction of the Kalpasar Dam across the Gulf of Khambat, an ambitious mega project under the government of Gujarat. So this project involved extensive field observations for various parameters like tides, currents, waves, wind speed, direction, temperature, humidity, radiation, and pressure. He played a major role in planning and coordinating different planned projects, such as the characterization of littoral transport along key sites along the Indian coast for sustainable shoreline management, which is aimed in the development of the National Sediment Transport Rate Atlas for the Indian coast. Dr. Basanta Jena is a panel member, reviewer for scientific journals such as Current Science, Ocean Engineering, and many more, and professional bodies, technical committee member of different organizations under the Ministry of Earth Sciences, other state and central governments such as the Integrated Coastal Zone Management Program, ICZMP, the Central Water Commission, CWC, Indira Gandhi Center for Atomic Research, IGCAR, DBCP, etc. He is also very actively involved in numerous industry-sponsored projects related to marine and coastal development works. He has published more than 50 scientific research papers in reputed scientific journals and conferences, authored 11 books and manuals, 69 conference proceedings, and 179 technical reports. Dr. Basanta Jena was actively involved in sponsored and industrial consultancy works, which involves about 35 marine and coastal ocean observation projects, 20 bathymetry survey and engineering projects, 75 projects for port and harbor, and 20 projects covering sediment transport and coastal engineering design, creek and inlet dynamics, etc. And moreover, he has also worked on about 25 projects for that involves the coastal zone management, and 4 projects involving the Indian Ocean high frequency radar. So he has guided many students for their project works and also very actively participated in several invited talks and training workshops. His research interests cover wide areas such as coastal and ocean observations, bathymetric survey for the exclusive economic zone of India, HF radar for the surface currents and waves, shoreline management plan and policy making, wave, tide and current atlas for the North Indian Ocean, coastal sediment transport model, and observational studies. Dr. Basanta Jena is presently the General Secretary of the Ocean Society of India for the year 2020 to 2022. And he was awarded the Certificate of Merit for his outstanding contributions in the field of ocean science and technology in the year 2012 by the Ministry of Earth Sciences, Government of India. So with this brief introduction, it is my proud privilege to kindly invite our speaker, Dr. Basanta Jena, to deliver the talk. The participants are actually requested that the questions and answers will be attended after completing the talk, and the questions can be messaged in the chat box. Thank you very much. So now I request actually Dr. Basanta Jena to deliver his talk.
Thank you, Dr. Prasad, for giving such an elaborate description about my works. So thank you very much. And thank you, OSI, to giving me this opportunity to deliver a talk today on Indian Coastal Ocean High Frequency Radar Network, that is called ICORN of India, and its applications. So thank you all. And so I'll just briefly, as you are aware, this is a part of Indian Ocean Observation Network called OON of National Institute of Ocean Technology, operates and maintains a network of high frequency radar system along Indian coast, known as Indian Coastal Ocean Radar Network, that is ICORN. It is a land-based remote sensing system capable of measuring surface currents as far as 200 km from the coast and waves and wind direction nearly 100 km offshore. The HF radar utilizes electromagnetic waves in 3 to 45 MHz frequency band and uses Bragg scattering principle to deduce the oceanography parameter. ICORN recently operates and maintains high pace, the 10 sites along a long range system, which is about 5 MHz. We operate 4.4 MHz system, which I will describe in my talk, which covers the 4 states and Andaman and Nicobar Islands. This system operates a spatial resolution of 6 km and temporal resolution of 1 hour. And this data disseminated by the Indian National Center for Ocean Information Service, that is called INCOIS Hyderabad, for this scientific and maritime operation. The potential of a HF radar system are enormous and can be employed in various aspects of operational oceanography and its research applications. So with this introduction, I will be presenting just introduction of what is ICORN and its data. It is now we are 14 years, more than 10 years, 1 decade of service we are into this field. And analysis of HF radar data at NIOT and other institutes. Then validation of HF radar and its applications for different research topics and what is the outcome so far and how we can way forward for further. So introduction, just I will tell about the history and the concept of this system. As you all may be aware that 26 December 2004, India hit a mega tsunami. After that, Ministry of Earth Sciences has initiated so many ocean observation programs. One is the bottom pressure recorder, which is our ocean observation system at NIOT. They are operating and maintaining, and data comes to INCOIS and NIOT for various research application purpose and to give dissemination to the local authority. Similarly, this high frequency radar around 5 sets has also been procured and installed and maintaining from since then. And apart from these two, there are so many current meter moorings has been deployed for this purpose, and the entire tide gauge network along Indian coast has been established. So what is this HF radar and why we have to do this? And as you are aware, I have told this is the online mapping of surface currents fields in a spatial distribution and the wave direction of spectrum. This is nothing in water. Everything is a non-contact sensor. Everything in the land we have installed very close to the system. I'll come the installation of HF radar in my next slides. Then this is the individual instruments are very expensive to deploy. You may be aware that for oceanography application, we go for current measurement means we have to go with a single point current meter or ADCP. You have to deploy at a single location, and that required boats. And then we can get only the current information at that point. Whereas this HF radar can give you the thousands of current meters equivalent to one system itself. Then these instruments measures the currents and at a special distribution, as I told, and also it gives waves and wind direction, let's say. And you know also that the satellite based observations are also not correct. So this HF radar gives the validation of satellite observation and other modeling work. This data can be used very well. Then how this HF radar works? This HF radar is, as I told, it emits that electromagnetic waves, the high frequency waves from a land-based antenna, that is the transmit antenna, and the some that is a known frequency. So it has a certain known wavelength we know, and that reflects, get reflected and dictated by a receiver antenna, which is also co-located at nearer to this transmitter at the same system. So this receiver antenna also receive the same frequency, which is in order to the brass scattering, and the current speed and directions are estimated using this Doppler shift. Here in details, what I want to tell you is that when we are transmitting a electromagnetic signals in a very narrow band, it gets touched into the sea surface, and it travels salinity as a media, that so it travels beyond the horizon. And if there is no disturbance in the ocean, so if no current, no waves, no wind, nothing, then we should receive back our reflected signal as a half of the lambda. But where that in this upper panel, it shows that if there is no disturbance in the ocean, that what is that our transmitted wavelength lambda should reflect back a lambda by 2. Whereas the ocean is not like that. It has so many disturbance due to wind, waves, currents, etc. So what is happening? So due to that, either current is moving away from the antenna or coming towards antenna. You see the bottom panel, that is the red things. So there, if it is that currents are coming towards the receiver antenna, it is positive, and it is going away from the antenna, it is negative. So based on this shift and using the Doppler shift, we calculate the current speed and direction from that which place it is coming back, their bearing and the patch bearing, all these things are measured accurately as because our RX antenna and TX antenna are geocoded with latitude and longitude accurately. So coming to this in a different picture to show this is at a remote site. As each remote sites we are shooting 1024 sweeps is a continuous sweep pulse on and off. So with this we are generating so many spectra. So this is the first order spectra and this is the second order spectra. So from the first order spectra, as I told, we are estimating the wave currents, and from the second order spike we are estimating the waves. So this is the in details. If I tell that this is the our first order peak from the spectral information, and this is also the second spectra. And this first order spike, whether it is moving towards receiver antenna, so is called positive Bragg's peaks, and if it is going away from this antenna, it's called negative Bragg's peak. So from this, the difference, we use the music, that is multi-signal classification algorithm, to find out the direction and from the Doppler shift we find the currents. So current speed and direction are estimated from the first order spike of the spectral information, and similarly this second order peak we estimate the waves. Coming to this, we have different types of this HF. We are using CODAR. This CODAR is nothing but a coastal ocean dynamic application radar. So there are so many other radars are also available called Vera, which is the German-based system, and CODAR is a US-based system. And these both are having a different principle. So I am talking basically on the CODAR. So CODAR has three different types of radar. One is standard system, high resolution system, and long range system. So this has a special range of say standard range is 20 to 60 kilometer. This is user friendly. You can operate based on your frequency, which is say 11 megahertz to 27 megahertz. So based on that, your this kilometer range and in the spatial resolution, as well as the that onshore and offshore, alongshore and offshore range are fixed, and you can change it based on your applications. Similarly, coming to high resolution system, you can it can be 15 to 30 kilometer, and if you are using 40 to 44 megahertz, it can go even 15 to 20 kilometer only. Whereas we can reduce this range size to only 200 to 500 meter. And whereas the standard system we can go from 500 to 3 kilometer. So depending on our application, like you are going for a coastal application, better to use this high resolution of the system so that your grid size is reduced to 200 to 500 meter. And long range, we are as these systems are, we are positive for this tsunami warning and other oceanography applications. So we are operating at 4.4 megahertz frequency, which we are getting sometimes up to 200 to 220 kilometer range. And in offshore as well as longshore, we are getting around 200 to 250 kilometer. And we made a grid size of a 6 kilometer range. So this, I'll be coming to that. This is the in details. So here I have put the frequency 5 megahertz, 13 megahertz, 25 megahertz, 42 megahertz. This 5 megahertz called a long range, and 13 to 25 megahertz called as a standard range, and 42 megahertz are called as a high resolution range. And this is the wavelength. If you estimate on this around 60 meter, 23 meter, 12 meter, and 7 meter. Based on that, your wavelength lambda by 2, what is the reflected signal due to Bragg scattering, is 30, 11, and all. This is the known frequency. And our time period is 4.4 seconds, 2.7, and 1.5 seconds. So this is your say transmitting antenna, which emits the electromagnetic signals, and it touches down that sea surface. and travels beyond the horizon using the salinity as a media, and it reflects back with lambda by 2 to our receiver. So this is this principle. As I told earlier, when these currents are moving, this is only one system called as a radial currents. And for this, to get that total currents, we required one more system. I'll come on to that. So radial current means this currents are, you see, this is the green color is coming towards, this is coming towards, this is going away from that. So when you here, you see this the spectra when we are plotting here. The green color is positive, blue color also is a positive, whereas this pink color is negative. So from this Doppler frequency, we can able to estimate the current speed of the things. So this is called as a radial currents. So coming to this, similarly, we can add one more system in nearby to that, so that we will get one more current as a different. It is coming towards and going. So both together, we can have a resultant currents, which will give the current speed and the direction. To fix this two system, we have a certain principle. We have to fix that coastal length, distance, and all these things we have to come into accounts. I'll come one by one. First and foremost is the cross angle should not greater than 15 degree or less than 165 degree. Otherwise, our coverage will be reduced drastically. So we will be spending a lot of money, but we will not getting the correct data. So in this reason, this is the at this point we have to be very, very careful when installing the things. One more thing, so the site selection for installing this Hfdr is very, very important. So you have to see that our systems are utilized properly. So from installation, the site selection stage itself, you have to be taken care. So if it's like this system, better to use not long range system here. You can use the standard range or things depending on this D. D is the distance from the one radial site to another radial site. So this is the formula, is D is equal to 40 to 60% of the R. The range is say 200 kilometer, means we can go up to 100 kilometer this distance. If you go more, we will not get the proper coverage with good quality data. So this is that what I want to tell you is this radial to total current, how we are converting. As I told, this is only one site called radial sites. It is the Kalpakam, which is covering almost 220 kilometers. And this is the Kadalur. This is south of Kalpakam, 100 kilometers apart. And this is situated in Tamil Nadu. If you just this both if you combine, we will get like this, and we will get a total vector. This is the current speed and direction, and this legend is provided here. And this is every 6 degree by 6 kilometer by 6 kilometer grid pattern, covering almost 220 kilometer. And this is also reducing. I'll come due to environmental impact on daily basis. So that I will show you later. This is in for a better clarity. Just I have given at same sites we have a software. Before we go to site, we just check at the DEX itself. How best we can get a good coverage. You see, this is the best coverage we could get. But if you reduce this distance, you will not get only this much you will get. And if you go away from also, you will not get any coverage. So this is very, very important to site selection. Apart from this, we have to see that whether no high power tension lines are near to your site, no structures, big iron structures are not there, and so many other that ferromagnetic materials which will impact on our data collection, data quality. We have to look into the matter before installation. Then these all are I have told you how the we can measure that current speed and direction from a HF radar. Coming to this wave observation using HF radar, this is very, very important nowadays because you may be knowing the cyclones time. This is very helpful. I will show you so many cyclones are measured by using HF radar. So what is the principle? So just to give an introduction and idea, the C-Sonde is the compact and high frequency radar system operated from the coast or any offshore platform also you can put it, which will provide you the current velocity map as well as the directional waves spectrum. Wave information is obtained from the second order radar spectra, what I told you earlier. And there are two methods are available to estimate the wave information from HF radar. One is the integral inversion method, and one is fitting with the model of the ocean wave spectrum. So basically, you are using this wave spectrum method to estimate this sea sonde wave data from long range system. And I will tell you here, this HF radar has some limitation for measuring the low waves. This long range system cannot measure up to 1.4 meter wave heights. So more than 1.5 meter wave heights it can measure. So it is very, very useful during cyclone and storm surge time. So this, as I told, this can measure wave height, wave period, wave direction, and wind direction. So these standard systems that can be measured in lower wave heights, as I told, 13 megahertz can measure up to maximum 7.4 meter wave height, and it can measure. It cannot measure up to 0.4 meter wave height. 40 centimeter wave height below it cannot measure. Similarly, for long range, it cannot measure 1.4 meter wave heights, whereas it can measure up to 20 meter maximum wave height, up to 20 meter. So similarly, this is the, as I told already, the theory. We are using this spectral wave theory for estimating these waves. The details are there in that also that CODAR websites. And now we are upgrading this system. I will come to that. We can able to do this raw data. We ourselves can also estimate the waves, height, wave period, wave direction, etc. And one important things I want to tell you here, this not only the wave measurements using HF radar is not like other conventional wave measurements. This also measures like a radial wave. Every that grid we have selected 6 kilometer or 2 kilometer or things. Even though your current meter range is up to 200 or 220, whereas waves will measure up to 50% of the range. So up to 100 kilometer, say like that. And it is a conical shape, the outcome when you are comparing wave data of HF radar with your model output or some other things, you have to have a similar circular pattern with a conical way to estimate the wave height and wave direction. Here I given the example. This you see here each grid how your circular manner is calculated, and the center point is taken as our output of the waves, and here a plotted onshore and offshore wave heights, and it is also compared with the wave radar buoy, which is matching very well. And this is that what I have told you, that we are getting the wave information from the second order peak. And here some of the examples I have given, which I got from that US website. And this is our website. We have compared one of the sites, 6 kilometer, 12 kilometer, 18 kilometer, 24 kilometer, how the waves are varying, and it compared with that our wave heights. Then apart from this currents and waves, wind and all these things, one more thing is capable this HF radar is to measuring the tsunami signature. So the tsunami, how it measures the difference in the current pattern. So what it does is it is from the second order nonlinear that it is using. Then from the surface height, it calculates the that water particle speed. That is when it is you know that as a current speed is uniform throughout that earlier to the tsunami arrival. When tsunami is arriving to the coverage of the radar, the current speed will reduce drastically. So that will give some a signal to that our central sites, and with that we will alert and see that whether signals is false or right. Accordingly, we can also check it with INCOIS things, and this data also online given to INCOIS. They can correlate with the other BPR and other system whether it is right or wrong. So before giving to the things. And this is the example. As I told, when a tsunami signature coming to the radar location, it is the speed will be reduced drastically, and it will give a signal to our central sites. With that, we can think. And 2012 Indonesia tsunami we could capture by our four-wheeler and hardware radar, and we have published also one paper on this. Coming to this ICORN, Indian Coastal Ocean Radar Network, in NIOT, we maintain and operate this coastal radar along Indian coast, and INCOIS is the dissemination of this data to all the scientific and student and research community. And we have a future plan for expansion of this system, as well as the upgradation and augmentation of the system for better utility of the data and research. So this is in as a sketch diagram. We have a system at Puri and Gopalpur, like Odisha coast, which are 100 kilometers apart. Coming to Andhra Pradesh, Machilipatnam and Yasyanam, again 100 kilometers apart. Tamil Nadu, Kalpakam and Kadalur, 100 kilometers apart. And Gujarat coast, Jagri and Vasiborsi lighthouse, it is opposite to each other with 90 kilometers apart. And Hardway and Port Villa, which is also 90 kilometers apart. All this data on real time, it comes to in NIOT Chennai as well as INCOIS Hyderabad, just between a 2 to 5 minutes difference. And this NIOT does daily monitoring 24/7 and regular maintenance of the central sites as well as the remote sites. And we do a preliminary QAQC. NIOT has brought out a QAQC manual, which is available in the websites of INCOIS as well as the NIOT. And we send immediately for repair and all. A lot of hurdles also we have faced, difficulty faced for maintaining this system, but still we are able to get a good return of the data. Similarly, INCOIS also is monitoring 24/7 for tsunami warning system, and they also do some secondary QAQC of the data, and they have also started a gap filling of the data. Then so many other research, in-house research for enhancing this data, and they do data dissemination things. So as I told, we have procured this system after that 2004 tsunami, but where we could able to get 2007. And our first system started installing on 2008 at Kadalur and Kalpakam. Then we moved to Machilipatnam, Yanam. And next year we have completed another 4 system, 2009. And Port Pillar and Hardway we completed in 2010. In brief, that sketch for the entire one remote site system is we gives the EB supply because it required a that is a main power supply to run the AC and all these things. And if power supplies are not there, we have kept also a generator which can feed to our system. Then we had some temporary side as well as some places to some permanent side are there. So that given to the power given to all these units. Then we kept some UPS system which can be after that we give to the power supply rakes, and that rake have that all these RX chassis, then computer, then TH chassis. For that we have also data transmission VSAT, then surveillance system, we kept the CCTV camera and display units and all these things, because all these systems are operated by only non-technical staff. It is only watchmen are standby there. Any major issue, we send engineer from here to maintain the sites. Otherwise, everything is operated from sitting at Chennai office itself. Through remotely. This is some of the photos of site selection and installation and testing. Before installation, we used to test like this temporarily, whether all data are coming good or not. It is suitable, this thing. And this is we do a calibration of the frequency. Whatever the frequency you are setting, whether it is receiving the same or not. This is called a transponder with we transmit with a known frequency and receive by the receiver antenna with the same things. So as I told, we are operating some of the permanent sites like this Kadalur, Tamil Nadu, both sites are permanent. Similarly, Andhra Pradesh, both sites are permanent, whereas other 6 are temporarily. Still, we are running with a container setup, and this is the REC. This is the RX transmit chassis, receiver chassis, display units, and it is a computer which is stores the data. All data comes through this VSAT. Every 1 hour current data, every 30 minutes wave data, every 10 minutes diagnosis file, whether it is working or not, it is transmitted here. This is the transmitter antenna, and this is the receiver antenna. And as I told, this has to be as close as to water line based on the frequency. So this should be not more than 350 meters from the water line at any pace. So these are our each sites, that is Yasanam, it is from Andhra Pradesh, and this is also on Andhra Pradesh sites at Machilipatnam, and this is Kalpakam, this is Kadlur, and Puri, Gopalpur. Then, as I told, Basiborsi and Jagri, both are the set up at lighthouses, both opposite to each other in the Gulf of Kambat. And this is the total achieved from these things. This is Gulf of Kambat. You see that Gulf is very high current zone, so this is looks very high because tidal range is very high over here. And this is the Tamil Nadu sides. This is the under Port Villa and under Hot Bay, Andaman sides. And this is the trends. And this is Odisha. This is Andhra Pradesh totals what we are getting every hours our sides. So status of data, we have more than 10 years. Like today, this year is 14 years of operation. This is the total our data recovery. We started 2008 March from this Kadlur, Kalpakam. Kalpakam, we are all the time more than 90 or 100% because the infrastructure provided by ICORN Kalpakam is very good. There is no power cut, nothing, no problem is happening here. So that's we are very good. Major issue we are facing is the power shortage and maintenance work due to remote sites itself. Then coming to Machilipatnam and Yasanam. Yasanam is very far from the any locality. So we have to have laid around 16-kilometer power cable ourselves for our things. After we all come to this power and all, now the tourism of these places is picking up, and that is another problem for our data collection problem. This is Basiborsi and Sigri. It is Gujarat, which and Gopalpur and Puri. Puri 2 times we hit by a cyclone, and data was there up to that landfall points. Then Port Biller and Hot Bay. If you see our this data return in recent years are very good, I can say. And this is the last year status, starting from December 2020 to December 2021. And this is the total. Total means our two-dimensional data are, this is the percentage. So I have taken a green are more than 70%, and yellow is 50 to 70%, and red is less than 50%. And as I told, the data dissemination done by INCOIS, they have a portal. You can log to there and go to this data information systems and go to Hfdr, Institute data and Hfdr. You can select any sites, and also you can request them by mail, and the utility, they will provide you the data. And any direct research or students are coming also to NIOT for doing this MTech or PhD programs. We are giving data to them directly because they are working at NIOT. And this is that one sample data, and they have put also availability of the data. These some gaps also they have noticed, and some gaps we have refilled again back to this. Coming to this analysis of this data, we have done in-house a lot of data analysis for our utility, as well as this data has been analyzed by various other institutes like INCOIS, IIT Bhubaneswar, then IIT Mumbai, NIO Goa. So anything we do, the calibration and validation are very, very important. But this Hfdr CODAR system has a unique features. So even you can get 85% good quality data using ideal pattern itself uh, without calibration. But where we do the calibration, as I told, we are using this known frequency that is part of operating your 4.4. Same frequency we are setting in a transponder. We are transmitting the same antenna, and we are going with in a circular way around that receiving antenna. So receiver is receiving all this frequency. We do some analysis how the measured pattern, and we see and then we put this measure pattern into this our data acquisition software. And what are the data collected? It checks that measure patterns capability and estimate the current speed and direction. Sometimes these measure patterns are distracted by the local disturbance, say, as I told, transformers, electrical faulty transformer, or high cable line, or any that electrical or iron activities are happening over there. So that again you have to do the recalibration of this measure pattern. So some of the sites things I have shown, this came very nicely, and some places we are getting distraction. Here, why I shown here is when we installed this shore protection work was not there. After that time, our data was very good. In 2015, due to arrest this sea erosion, they have put this sea wall, and which is above our antenna. Now, what we have done is we have brought our antenna very close to this sea wall. Then again, we have done this calibration, then put in that things. There we got a good quality data. So this is one more thing. This hard way, you see this type of structures also affecting this our measure pattern. So that we, as I told, we have to be very, very careful for doing this calibration of the system. Otherwise, we will not get a good quality data. Sometimes this jetty also we noticed the bigger ships when it comes, we had a problem. 2010 when we installed this was a full empty, no operation was there. Operation of this ship and started 2017, then we had a problem. Sorry. Now we are in touch with the local authority, and they provided a land. We are going to shift our total system 3 kilometers away from these sites. So as I told that sometimes due to this environmental effect, the ionospheric effect, in night time we are reducing our range. See, we are getting daytime in the same day, 21st June 2010, I upload around 219 kilometer we got. But whereas in night time, it is reduced to 50%, only 140 kilometer at scale. So this is also one of the effect, because a lot of people are informing that there is a gap in the data in Hfdr data. So this is the we cannot avoid this ionospheric noise when it creates. That time we will have to have a short range data. You cannot go up to 200 kilometers. It is 100 kilometers. Similarly, when it is 100 kilometer current, the waves also is reduced to 50 kilometer and also. These are the things we have to be. This is the limitation of the systems. And some more examples I have put again how the range has reduced due to even this location. It came less than 100 kilometer, 90 kilometer once. So these are the things that happen due to the ionospheric interference due to environmental conditions. So this is the, I want to show you here how without measuring how it can happen, and with measuring how we can improve the data. And as I told, without site selection, we can get a good quality data in the center of the person. Outside, we have to have some more filter to get a good quality data. Otherwise, here it will not get more than 85% confidence level. we also done some of the data analysis using this satellite image and that extraction from the satellite image Oscar data, the current speed direction, and compared with the single point current measurements and the HA product data. And these are the some figure I have put it here. We have developed some of the MATLAB code which we for extraction of various current, speed, and direction, and all these things like U component, V component. If any students wants any place, we can extract and give the time series data, current, speed, and direction, and we could able to reproduce the same thing which we got from this a black box software which is provided by the Coda, and ourselves we can regenerate these things. And I have analyzed some of the data analysis for different states of the U and B component of Andhra Pradesh, Tamil Nadu, from starting from the coastline to up to 200 kilometer offshore, the variation of different years and different time, special difference. And here I just wants to inform you that in east coast of India, you may be the knowing that the currents are transitional during February and October. And you see here between 2 days, entire current pattern is changing. This is the 11th February, which is current is going towards south, and it has a tendency to so that is 0. And you see in 13th February, 15th February, it is the entire current pattern has converted towards north. So 11th February, 13th February, and 15th February, between 2 days, 13 to 15, the current pattern entire east coast has been changed. And this is that your reverse progressive vector, when you plot in one current, you will come to know that things. Apart from that, we have also developed some program to gauge fill this data. So we have done with the total vectors, and we have tried to fill with using this neighborhood statistics. But later on, we came to know if you start gauge filling with radial currents, it will be far better. That what even inquiries also come up with some algorithm. And we have done some of the analysis for this using Hfdr for this tidal constants, then extraction of longshore current and offshore current using Hfdr data for various coastal applications. And I have done also, we are trying to do some current atlas. I will be coming to that. We have done this analysis. This is the year-wise current I have put one after another at a different location, all 4 locations. Similarly, here for the next 3 years, I have put, and we have analyzed the current pattern of different years, how it varies from the things. Then some of the research we are carrying out for this ED detection and tracking, upwelling and sinking, and some of the publication also has come, and this ED paper has come in the Journal of Geophysical Research, Oceans. Then coming to this validation, so we have done periodically, we are deploying that vibrator buoys and ADCPs and single point current meter in coverage area of HF and we are comparing. Some of the comparison I will show you here. This is one single point current measurements with HF data, and this is the waves height with vibrator buoy, and also we compared with our mic models. This is the some of the other locations at Chennai, this one. And this is at different rain cells during cyclone ward, how it is, the data has been captured by Kadalur and Kalpakam. And this is the Jal cyclone. Our that time one vibrator buoy was there of Chennai, we have compared. So which is matching very well with measured HF radar as well as the measured buoy data. And this is one more cyclone which is near to Kadalur. There also we had a buoy, and buoy Hmax and HF radar at a different range cells has been compared. And this is a Phalian cyclone at that Gopalpur. This also compared with the buoy measured data, which is matching very well direction and height. And then some of the research applications where I want to put here before now time is running short. So these are the various applications people can look. One is tsunami warning, oceanography studies, that is circulations. Then beach closure, that is our coastal erosion and accretion studies, water quality monitoring, fishery larva movements and other that potential fishery zones studies, climate research, that is green energy. It is very, very useful for disaster management, cyclone monitoring, oil spill monitoring, pollution monitoring, search and rescue, buoy tracking, then maritime safety and operation. This data is very, very important. If you have all along the Indian coast, we all can put this on live applications. In world, these are the percentage of utility of HF data in a different field. People are using more on the circulation and oceanography study. This data is a very big way. Second, coming to oil spill and pollution monitoring, search and rescue, beach closure, tsunami, maritime safety, and then slowly it is coming fisheries and all these things. So this data, HF data is very, very vital. Some of the figure I am showing here during cyclone, how the current pattern are changing. This is Thane cyclone, which is hit near this, southern Tamil Nadu. And this has gone in between our Kalpakkam and Kadalur. Not only this Tamil Nadu data, you see that even it has affected the Andhra Pradesh data also. And this is that one cyclone which hit near Gopalpur. That time we had a up to landfall, our buoy has worked. We captured that wave data, but due to Puri site was off, we could not get the total current direction. But whereas this is the radial current, we have a Gopalpur up to landfall point. This cyclone, even though crossed here and it is in started from this Andaman. So the Andaman current pattern has been changed. I will show you here. You see, this is before cyclone and during the cyclone and after cyclone. How this current pattern even impacted that cyclone, even southern part of the bay. And this is one of the Nada cyclone, which is again crossed in near Chennai, South Chennai, and our so many HF radar, 4 HF radar near to that has been captured. And this is the wave height of Kadalur and Kalpakkam and different rain cell. Then this is on our high resolution system, which is captured and Sinnakupam and Perandura, which is south of Kalpakkam. And this is that current pattern during that cyclone. And here I will show you between a 2 weeks time, 2 cyclone has been gone, and our sites was here one and here one. And you see how the current pattern has changed here. You see, remember that first cyclone when it was gone, the current was towards south. And when the second cyclone came, the current pattern, entire current gone towards north between 2 weeks time. So this is one significant observation we had in this our network, and the research are going on all these things. This is one more cyclone, is Gaja, that it hit Tamil Nadu, very a lot damaged, a lot of property and all. And this is Titli, again it is south of Gopalpur, and we have compared with Gopalpur buoy. The wave heights are matching very well, and this is the current pattern change over during Titli cyclone. And this is the recent one, cyclone Nivar, which is again Tamil Nadu sites. And we could get wave height, wave period, and wave direction very accurately and very precisely on our both Kalpakkam and Kadalur sites. And these are the research done by IIT Bhubaneswar. One Mr. Mandal is now awarded the PhD. He has used this data. He also compared all the sites, the variation of current pattern and waves during Ranu, cyclone Ranu. And as I told, we had some tsunami signature, the 2012 tsunami, Indonesia tsunami. And we compared with Padang and Hot Bay and Port Vila. This is our HF radar. This is their HF radar. So if you see we could get Compal Bay and that 30 centimeter height difference in that tsunami height. And Nankovary we got 12 and Port Pillar we got 5 centimeter. So this we have estimated from our Hfdr data. And one more applications I want to put in here is recent is going on. How to detect vessels or ships using Hfdr Doppler spectra. So you know this Doppler spectra is a continuous spectra. It is so this C echo first order we were using for current and second order using for the waves. But some in between some vessel echoes are coming. So using that, how to detect the different type of vessel and all. With the help of using that, we are going to do a trial basis in Kalpakam in next month. So in this also we have some limitation. It required a very big ships, which is our 1/4 of the lambda. That the height of the ship should be 1/4 of lambda. Then only we can able to detect a ship. So we are operating 5 megahertz. So around 15 meter height ship only we can able to detect. Otherwise, we have to use this high resolution 13 megahertz or 42 megahertz for detecting the 6 or 3 meter ships. So this a trial run we are doing now. This is one paper I have got from US. They are now written and it's possible for detecting. And now US has implemented for detecting ship along the Hfdr sites. And this is that they are targeting. This is due to ionospheric difference. But whereas you see this is belongs to ship echo. This are belongs to ship echo. So from this we have to analyze and find out how big it is and what is the height, what is the length, and we can able to track what is the speed of the ship, what is the bearing, which is heading towards. All these things can be estimated. So now with this data is available, so we have started one developing a surface current atlas for the east coast of India using Hfdr data. And we are now upgrading, as I told, to this our central sites. If that comes in place, maybe another 2 months time will be placed, which is very handy to analyze the data and disseminate the students or researcher and anything in real time mode in a better quality control and QC control way. Then if you see now what is the outcome of this program last 10 to 14 years is now utilization of ICORN data is going big way. There are so many research organizations and industries are using this data. As I told, benefit of this data is shoreline management studies, port and harbor management studies, tsunami warning, oil spill, subsidence risk, ship detection in coastal waters, scientific surface current circulation, wave data, wave current interaction, input and validation of the circulation and wave models. Hfdr can be an alternate to the satellite data at the coastal regions where satellite data is not available. And Hfdr can be used to shed light on the dynamics of the small EDs with its high resolution data and biological studies. So there are so many students as carried out internships and a lot of PhDs has come, a lot of technical reports has come and journals, proceedings, so many people come. You please go through this. And we conduct the workshop and training periodically. Now, due to this pandemic situations, we could not conduct 2018 onwards, but we had a workshop. 2010 is the first workshop. We had a 2019 also the second workshop. A lot of people have attended, and using this user interactive workshop, we could able to make the people to understand the and to utilize the data in a proper manner for their research work. And now we are aiming to use use this data on a real field for IMD, for storm surge and cyclone and tsunami purpose. And way forward we had a proposal to expand this network. 9 pair has been approved, but due to fund constraints, we could not do it. If 9 pair comes, this is our proposal we are going to install. But this is also not sufficient. If you want to have entire Indian coast and put in proper things, we have to have different types of equipments like 5 megahertz, then 12 or 25 megahertz, and or 42 megahertz for different ports. So total 24 pair is required to complete this, but 2024 is not possible. Thank you.
So thank you very much, Dr. Basanta Jena. It was a very inspiring and a very informative talk. There were many interesting things that you have brought out, specifically on the benefits of the Hfdr data. You started your presentation by giving a brief overview on the working principle of the Hfdr, covering aspects like the Bragg scattering and stressing upon the importance of the Doppler spectrum. You were actually showing the importance of the positive and the negative Bragg peaks in the data sets that has been collected. Thereafter, you covered aspects of the seesaw configuration, covering the standard, high resolution, and the long range aspects. And the radial currents, how it's estimated using the Hfdr, and how the resultant currents are also calculated based on a combination of radars which can be used in succession that has been demonstrated. There are very interesting things that you have shown for the Kalpakam and the Kadalur locations of this Hfdr. And also because it gives importance for both the surface currents as well as the ocean waves. I think you mentioned that it cannot measure the waves below 40 centimeters. No, that is one of the limitations. 40 centimeters and below, wave heights cannot be measured of it.
Yeah, long range, 1.4 centimeter we cannot measure, and in high resolution 0.4.
Okay. So I have a small question here. Actually, when I was because in the later part of your presentation, you mentioned about its application for tropical cyclone forecasting and detection. So we know that in tropical cyclones, you have very high wind speed. So is there any limitation on the wind speed and the wave heights that Hfdrs can report? Maximum limits.
Yeah, actually that maximum is not a problem for Hfdr, whether wind or waves. It can go up to even 20 to 30 meter wave height can be measured, and and these systems even can withstand 220 kilometer per hour wind speed during cyclone also. So that and it will give the correct data. So there is not a problem for that.
Yeah, that's very interesting actually. And also you have actually talked about the alerting mechanisms, especially for the tsunami waves. We can see that there is a decrease in the ambient current speed. So it's an indicator actually that there is something which is going to come. So that is really very interesting to see that actually. And in one of the applications that you are mentioning about the eddy detection and tracking, and also the upwelling characteristics of waters, I think that is going to be really have a lot of interest will be developed among the researchers using this data, especially to understand and track the eddies in the coastal regions. We have numerical models which can do that, but the data from this Hfdr can go and supplement their numerical models to improve the quality. I think that is going to have a very significant impact. And I have a small question like from your presentation. There are some couple of questions also in the chat box. You mentioned actually about the wave observations from the Hfdrs, and you will be fitting it to the wave spectrum. One of the way of doing it is one is the inversion method, the other one is fitting it into the wave spectrum.
Yes.
So which wave spectrum is basically used in this region actually, like in the coastal areas? Is it the John Swap or any other modified wave spectrum which is used?
No, John Swap only. Actually, that you can also, if you know your wind wave pattern spectra, you can fit to this our central server as a site specific, so that you will get a better quality data also.
Okay, that is very good, actually. And in one of the slides, I think in this slide or before slide, you were actually showing about the proposed network of Hfdrs that can come in the future. So is there any plan to have any Hfdr in the West Bengal coast? Because especially in the Sundarban region.
Yeah, here one is there, you'll see here.
Okay, so this can cover the Sundarbans area also.
Yeah, it is covering Sandheads and Sagar Island area.
Okay,
Not,
that is very good.
yeah.
Okay, fine. So I think I am done with mine. Let me go to the chat box. There are, I think, some couple of questions that I have seen. Yeah, the one question was from Dr. Mani Murali. The question is, how far from the coastline we can have the currents or the wave data?
It is 6 kilometer from the coastline. This long range data. Because the first grid is 6 kilometers, so that 6 kilometer grid has some problem due to the coastal things. But when you use this high resolution like 25 megahertz, we can even have 200 meter from the coast.
Yeah. Okay, fine.
And if you have 45 megahertz system, you want 75 meter from the coast, you can have a current data.
Okay. Okay. Now, there's another question by Umakanta Pradhan. So the question is, can we get the longshore currents from HF radar system?
Yes, I have shown one longshore current and offshore current, how we can extract from the HF radar. One slide is there. I have shown it.
Okay, fine. That's fine. And I think the one there's a last question actually from Professor Vimlesh Pant, IIT Delhi.
Okay.
So the question is, how the subsurface currents are derived from HF radar data, and how good are these derived subsurface currents when compared with ADCP measurements?
Yeah, actually, I have gone in detail. If this surface current HF radar data is only from surface to 2.5 meter only. So this surface current is very well is wind and wave driven currents. So that's why it is a totally surface current, which is comparable very well with if you apply a drifter of 2.5 meter feeder. If you attach on that, it will match very well with the surface current data, drifter data with HF radar data, because it is only tops 2.5 meter data. Okay. Yeah. But ADCP, I would like to inform him that ADCP cannot measure the surface current, 2.5 meter surface current. But we have compared ADCP data, which is 5 to 10 meter below surface, which is matching that trend. And we have put a surface drifter, which is matching the trajectory when you take a drifter plus HF radar trajectory, which is matching very well.
Okay. Okay. So thank you very much. I think these are the questions, and there are appreciations actually also from the participants about the talk. So it was really a very wonderful talk. It's very informative and very important area that we need to stress upon in the future, because I definitely feel that the researchers and the scientific community will take into account the capability of the HF radar data for their research purpose.
Thank you.
So on behalf of the Ocean Society of India, I thank actually Dr. Basanta Kumar Jena for this very informative and interesting talk. Thank you very much.
Thank you. Bye. Yes. So bye, Prasad. Thank you for opportunity.
Yeah. Bye.